In the second part of this lesson, we are going to see how you have to sometimes use integration by parts more than once in a problem in order to get the antiderivative. And then we're going to try to use integration by parts to find one last missing antiderivative that we kind of skipped over earlier in the year. Okay. First off, the antiderivative of x squared cosine of 4x dx. Again, look for u sub first. Does the derivative of the inside exist here on the outside? Well, no. The derivative, that's the thing that's on the outside, the x squared, is more complicated than the derivative of 4x, which means we won't be able to get rid of the x squared and u sub won't help. Remember to think about that first. So the next thing we try is u substitution. Sorry, we just tried u substitution. The next thing we're going to try is integration by parts. If we can break up this product into two pieces, one piece that is easy to integrate, and another piece that gets simpler when we differentiate. Right? We want a derivative to make things simpler, and an antiderivative that we just need to be able to do it. It doesn't have to make things any better. We just have to do it. Then integration by parts might help us. And that's what we have here. The x squared, I know it doesn't completely disappear with a derivative, but it does get simpler. We go from a quadratic to a linear, so that's progress. And the cosine of 4x dx, we can integrate that. It's not hard to integrate a cosine. So if we call our u x squared and our dv the cosine of 4x dx, we've got the setup that we need for u substitution. So let's try that. The differential of u is 2x dx, and the antiderivative of the cosine is the sine. But be careful about that internal, that simple chain rule there, that 4x in the inside. You need to make sure to divide by that 4. And that's our antiderivative. So if we set up our u substitution here, we can say that the integral of u dv, of course this is always going to be where we started, so you don't have to think too hard about what you're writing here, is equal to, I'm just going to apply the formula, uv x squared sine of 4x over 4 minus the integral of v du. Notice one thing that happens here is that 2 over 4 can reduce, and we're allowed to do that as much as we need to. So the 2 over 4 will reduce to 1/2. And we still have an integral whose antiderivative we don't know off the top of our heads. U sub's not going to work for the same reason as before. This x is a little bit stubborn. It's not going to go anywhere if we try to take the derivative of the inside. But this is almost the same setup as before, where we can still take our antiderivative and think of it as a product of two pieces, one piece whose derivative is nice and simple, and another piece that is easy to integrate. Sorry, I should include the dx on that. So what we're going to do is go back to the drawing board with our u substitution and start again. This time, the u, the part that's easy to take the derivative of, you can choose whether you want to put the 1/4 or the denominator. You can choose whether you want it with the u or with the dv. It doesn't matter. So the derivative of that would be 1/4 dx. And the dv, the factor that's easy to integrate, is the sine of 4x dx. And the antiderivative of that, our u, would be negative cosine of 4x over 4. And so here's where we have to be a little bit careful about signs. I'm going to start from the scratch here. We're looking for this, the antiderivative of x squared cosine of 4x. So what we want to be able to do is simplify everything on the right-hand side there. The x squared times the sine of 4x over 4, that's still here. That's not going anywhere. But what we can do is take the antiderivative of x sine of 4x over 4 dx and replace that with uv minus v du. uv negative x cosine of 4x over 16, because those 4's work together, minus the integral of v du. Negative, and by the way, the negative in here, in front of the cosine of 4x from my v, well, I can just cancel those two out, because I can pull the negative out of the integral whenever I want, times the cosine of 4x, that's the v du, notice how, again, I have two 16s there working together. And now I've gotten to an integral that is easy to simplify. So I can, stuck here with this x squared times the sine of 4x over 4. That's not going anywhere. Minus negative, and remember to distribute this negative. It's really easy to overlook that, but this negative needs to be distributed. So that would be plus x times the cosine of 4x over 16 plus the antiderivative of the cosine of 4x over 16. Remember, I'm sorry, I forgot about the distributing that I just talked about. That's now a minus sign. The antiderivative of the cosine of 4x over 16, the over 16 doesn't make things more complicated, and I can take the antiderivative of cosine of 4x. I just have to remember to multiply the denominator by 1 more 4. And usually you're going to end up with no like terms, so there's not really anything else left to do. And that's your answer. It looks long, there's a lot going on, but that's it, and it's going to be fully simplified. I certainly could make a common denominator if I felt like it and put them all together into a single fraction, but there's nothing I'm going to do to make x squared sine of 4x and x cosine of 4x and sine of 4x be like terms. So since I can't combine them anyway, I'm happy leaving them the way they are. Okay, we're going to try one more example here. And if you remember, when we learned our derivative and our antiderivative rules, there was one that we skipped over, like it was a glaring omission. We learned the derivative of e to the x, the antiderivative of e to the x. We learned the derivative of ln of x, and we never talked about the antiderivative of ln of x. Well, now we can do it using integration by parts, because the antiderivative of ln of x dx is asking for the antiderivative of a product. What's that you say? Ln of x is not a product? It's just one factor? Well, sure, if you think of it by itself. But if you separate it from the dx, now we can think of it as two different factors. One of them, the ln of x, is super easy to differentiate, and more importantly, it gets simpler, sort of, when we differentiate it. And then the other factor, the dx, is easy to integrate. You might not have guessed this one going into it. That's okay. But let's see what happens when we try it. If we think of ln of x as our u and our dx as our dv, like I said, we can differentiate ln of x. Its differential is, since du dx is 1 over x, du by itself would be 1 over x dx. And dv, sorry, the antiderivative of dv is v, and the integral of dx is just x. So we can set this up as the antiderivative of the ln of x times dx, that's our u dv, equals uv minus the antiderivative of v du. Well, look what happens when we put the v and the du next to each other. The x times 1 over x cancel out, and we're just left with dx. And so we can take that last term and just rewrite it as the antiderivative of dx, which is just x. And so the antiderivative of ln of x dx is x ln of x minus x plus c. And if you want to, you can try the next one on your own. It's on the same page because you use a similar strategy to take the antiderivative of arc sine of x. Treat arc sine of x as your u because we know how to differentiate it, and treat dx as the dv and see what you can come up with.